Besfort Ons seminare online anglish nuk e di çfarë gjuhë shef nësh okay. Trajnojmë gjuhë shqipe atëherë. Por megjithatë fillim me gjuhë shqipe, mirë se vini në seminarin e radhës të departamentit. Folësi sotëm është Besfort Shalaj nga Universiteti i Bristolit, I cili do na flet për the probabilistic Zeta Function on a finite lattice. Jam shumë I lumtur që më të kështu, është profesori I një shkollë në mesme që ka marrë pjesë në kuptohet në udhëzimet dhe ngritjen e Besfortit, kemi kolegë të departamentit zakonisht, shefit e tjerë, edhe kemi folësin e radhës, por të fundit, po më të rëndësishme të kemi studentët aktual në departament, kështu që Besforti do të flet një 50-55 minuta, pastaj mund të bëjmë pyetje, por nëse keni ndonjë pyetje, derisht e kemi në Besforti fjalën. So it gives me great pleasure to introduce today's speaker, Besfort Shalaj from the University of Bristol, who will be speaking about probabilistic Zeta Function or finite lattice.
Okay, so I'm going to talk about the probabilistic zeta function of a finite lattice, and I'm first of all going to give some motivation. So we're going to start with a group G, and we're going to let P of GS, where S is a non-negative integer, be the probability that a randomly chosen S tuple of elements of G generates G. Okay, so by randomly I mean uniformly at random. So I just take all the S tuples which generate G divided by the number of all S tuples and I get the probability. Okay, so I think this is a fairly natural thing to look at and to possibly get a description of this probability in terms of the group G. Okay, so for now S is going to be a non-negative integer, but later we'll extend P of GS to the entire complex plane, and then 1 over P of GS will be the probabilistic zeta function of the finite group G. So I guess I should say G is a finite group and all objects in this talk are going to be finite. So the reason for this is that, well, if you look at 1 over zeta of 2, where zeta is the Riemann zeta function, this has a probabilistic interpretation, namely it's the probability that 2 randomly chosen integers are co-prime. But in terms of this, there's a very cute identity. So 1 over the Riemann zeta function is the product over all primes of the probabilistic zeta function of the cyclic group Z modulo PZ S, where P runs over primes. So why is this? What's the probability that a randomly chosen S tuple of elements of the cyclic group generates the group? Well, it's 1 minus 1 over P to the S, because every element of this group generates the group except 0. So the only way that you will get something that doesn't generate is if you choose your S tuple to consist of all zeros. And that's precisely the probability that you do that. So 1 minus that is the probability that a randomly chosen S tuple generates the group. Okay, so this is just a cute identity. I mean, there really isn't much to it, but it sort of gives an excuse to call this thing the probabilistic zeta function. Okay, so let's try to understand this POGS. So if I just look at the number of S tuple of okay, so if we just look at the number of all S tuples of elements of G, then this is their number. And if you take an S tuple of elements of G, then it will generate something. It will generate some subgroup. So I sum over all subgroups, and then what do I have here? Well, I'm just partitioning the S tuples of elements of G according to which subgroup they generate. Okay, so what's the number of such S tuples which generate H? Well, I take the probability that a randomly chosen S tuple generates H, and then to get the number, to get combinatorial information, I just multiply by the total number of S tuples of elements of H. Because if the elements of H, if elements of G generate H, then in particular they lie in H. Okay, so this isn't doing anything. It's just saying if I have an S tuple of elements of G, it will generate some subgroup. Okay. And now, if you've seen Mobius inversion before in number theory, this is the perfect setup for Mobius inversion because we have something simple here and then something more complicated, and this is the thing that we want to understand. So it would be nice if we could somehow invert things and get information on this. To do that, I'm going to take a slight detour and talk about Mobius inversion on both sets. And this is due to Hall, who did this in 1956. Okay, so let it be the opposed set. So this is a set, the partial order. So a binary relation which is reflexive, antisymmetric, and transitive. Okay, so I guess we'll say P with a partial order less than or equal to. Okay, and again I'm in a finite coset. Everything will be finite here. So if I have two functions f and g, which say are complex valued, such that f of x is given by the sum over all y less than or equal to x of g of y. So I have something similar as to here, or maybe if you're thinking in terms of Mobius inversion, then I take the coset to be the divisibility coset. So then I have something like f of n as the sum over all divisors of n of g. Okay, so this is likely something that you've seen before, and it's just a special case of this more general set. Okay, and how do we invert this in number theory? Well, there's this Mobius function, which gives g of n as basically a linear combination of values of f. So again, we have a sum over all d dividing n of mu of n over d times f of t. Okay? So we would like to do something similar. We would like to do the same thing here. So we want Mobius function mu from p to b, let's say sum over all y less than or equal to x of mu of y of x times f of y. Okay? So I just want to find such a function. I don't know what this function is right now, but I just want to find such a function which allows me to invert this. Okay? So how do we find it? Well, there are more conceptual ways to think about this, but we can just sort of brute force it. Let's plug in the definition for f. So we have sum over all y less than or equal to x of mu of yx. So right now, just think of mu as being any function. And I'm doing something with it. And then f is the sum over all z less than or equal to y of g of z. Right, just by this. Okay, and now I interchange sums. So I have the sum over all z. Z goes up to y, and y goes up to x. So z goes up to x. And then I have g of z. And then I have the sum over y. Y is at least z because now I've fixed z. And it's at most x. So mu of yx. Okay? And I want this to be equal to g of x. So let's bring g of x out, and I get g of x times the sum over all. Well, I don't get a sum. If z is equal to x, then the only thing between x and itself is x. So I get mu of x, and then I get the rest. So z now less than x because I pulled z equals x out. And then again I have this sum. Okay? And I want this to be equal to g of x, so I'm going to set this to be 1 for all x in the poset. And I want this thing to just be 0, so I'm going to set this equal to. And what this does is that it gives a recursive definition of the Mobius function. Okay? Because I have set the Mobius function to be 1 on the diagonal of p times p. So mu of xx is always equal to 1. And then here, once I have mu of xx, well, if so maybe it's worth writing this out. So if if y is strictly less than x, then I have mu of y x is equal to minus the sum over all z bigger than y less than x of mu of zx. Okay, just by just by taking this to the other side, and then if so, I already understand what happens on the diagonal, and if it's not on the diagonal, if y is less than x, then I just use this relation because I've assumed that I've previously defined everything here, so the right-hand side is defined, and this gives me a recursive definition. Okay, so now I've recursively defined Mobius function mu, which allows me to go from this relation to such a relation. Okay, so it's sort of inverting.
Yes. Could you just recall the definition of classic sense? Because there you have seemingly one variable, but in fact you have two, and then what's for the arguments square free and not square free.
So the reason that happens is that well, I think I'm going to discuss this when I talk about the divisibility lattice. But the details aren't that important here. The idea is more important. I just have something like this, and I want to express g in terms of f. I want to invert. So now, more generally, I have a coset, a set of the partial order, and then I have something like this, and I want to invert it and express g in terms of f. That's all that's happening. Okay, and now I have such a function. So let's return to our setup. We have G power S is the sum over all subgroups of G of P of HS times the order of phase to the power S. And now, the post set here, I take to be the subgroups of G with the partial order being being a subgroup. Okay? So now I now have a function which allows me to invert this relation. So if I apply Mobius conversion, then I get, well, the right hand side, so P of GS times G to the power S, which is just what I have here. Then this is equal to the sum over all subgroups H of G of mu of HG, which are just these Mobius numbers coming from this whole set. And then the left hand side I have the order phase to the power S. Okay, so I've just used that Mobius function and I've used the Mobius function to invert that relation, and I get this. And now just dividing by G, the order of G to the power S, I get P of GS is the sum over all subgroups H of G with mu of HG divided by the index of H in G, right? Because when I divide by G, then things work out. And so now this is a Dirichlet series. It's a finite Dirichlet series because I assume the group is finite. So if you don't know what the Dirichlet series is, then it's just something like that. Okay. And it's a Dirichlet series because these are integers by Lebronc's theorem. Okay, the index of a subgroup and the group is an integer. Okay, so maybe it's helpful to do an example where we demonstrate how Mobius inversion works. Because the definition is sort of complicated, especially if you think about it like this. So let's just take a simple post set. Say we have a bottom element. Let's say we have two elements A and B. Maybe they have something like this, and then maybe there's another element here. Okay, so this is a post set. I've given its classes diagram, I guess. So it just means A is bigger than 0, B is bigger than 0, and C is bigger than A. So C is bigger than 0, everything is constant. Okay. So this is just the Hasse diagram that you see in high school. Okay, and suppose that I want to find the function mu of x, where x is going to be one of these elements with respect to the top element, right? Because here mu is a function of two variables, so I'm just going to fix the second variable to be the top element, and I'm going to find the Mobius numbers. So how do I do this? Well, mu of 1, 1 is equal to 1 by definition. And then this recursive definition just tells me, well, look at everything that's above, sum all the Mobius numbers, and then flip the sign. Okay? So mu of C1, I look at everything that's above, the only thing that's above is 1, the Mobius number 1. So that Mobius number 1 is there, and I flip the sign so I get minus 1. And similarly, mu of D1 is minus 1 because there's only one thing on top. Mu of A1, well, I have a Mobius number of -1 here, a Mobius number of 1 here, and I look at everything that's on top. So I get -1, +1, and then I flip the sign. But that's just 0. Okay? And similarly, mu of b, 1 is 0. Again, because the only things that are on top are c and 1, so I get -1 +1, that's 0, I flip the sign, I get 0. And then lastly, mu of 0, 1. Well, I look at everything, because everything is on top of 0. So now I guess I have a 0, 0, and I have a -1 here. So I get 0, 0, -1, -1, +1, that's -1. I flip the sign, and I get 1. Okay, so this is how Mobius inversion works. Just look at everything that's on top, sum everything, and flip the sign by the recursive definition. Great. So now, just to make sure that we're all on the same page, I'm going to talk a little bit about lattices. So, what's a lattice? Lattice is a coset L with a partial order, so it's a set with partial order. Again, reflexive, antisymmetric, and transitive, such that for any x and y in L, there exists a unique supremum for x and y, which I'll call the join, and write it like this. And there exists a unique infimum of x and y, which I'll call the meet, and write like this. Okay, so if you've seen this before, great. If not, then it's a useful thing, because many structures have a lattice structure. Like if you look at the space of all continuous functions, that is a lattice where you just take the join of two functions to be the maximum and the meet of two functions to be the minimum. Because you insist on being continuous where they meet, then it's going to give you something. So many things have this structure. Let's just look at some finite and nice examples. If I just look at something like this, then it's trivially a lattice. Perhaps it's more helpful to look at an anti-example. So something like this. Then let's name this A, B, C, D. Well, C and D don't have a supreme at all. There's nothing above C and D. So I need to add something. Let's add 1. Now C and D have a supremum. A and B don't have an infimum at all. There's nothing below A and B. So I'm going to add 0. And now I have an infimum. But now, this is still not a lattice, because if I look at A and B, then C is a supreme, is an upper bound for both of them. C is above A and C is above B. And so is D. D is above A and D is above B. But C and D I can't compare. C and D one not smaller than the other. So there isn't a unique supremum, or many supremums. There are at least 2. So this is not a lattice. I want something where the supremum exists and is unique, and the infimum exists and is unique for all lattices. And by running the same argument, every lattice must always have a top element and a bottom element. A unique bottom element and a unique top, because of essentially the same argument. So I must always have something 0 And if you look at the Mobius function of the divisibility lattice, then this is precisely the Mobius function from number 3, which is what which is what I was trying to say before. And the reason why the standard Mobius function is sort of a one-variable function is because, well, I think of n as fixed. That's it. So this is still two variables, but I just think of n as fixed. So in the usual sense, I think of the Mobius function as just being a function of one variable. Okay, great. If there are any questions, feel free to interrupt.
So now the question is, what is the standard Mobius?
Yes. So the right-hand side is the standard Mobius function, and the left-hand side is the Mobius function that I defined. Great. So as with any sort of structure, we want to identify what are the building blocks for this structure. So this is not an entirely trivial thing, and different people view building blocks for lattices as different objects. But for me, the building blocks are going to be the jointly reducible elements. So if I have a lattice L and I have an element in L, then I'll say that this is jointly reducible. If I do manage to write X as a join of two elements, then A is equal to X, or B must equal to X. Okay? So I can't write X as a join non-trivially. I always have to use X. Okay? So I'll call such an element jointly reducible, and now if you think about it, you start with a finite lattice, you have an element. If it's jointly reducible, that's great, it's a building block. If it's not jointly reducible, write it as a join, and then ask whether the elements that you've written down are jointly reducible. If they are, great. If they're not, keep going down. And so, because of finiteness, you get a decomposition of any lattice element as a join of jointly reducible elements. So in that sense, they're building blocks. Okay, so maybe let's look at another example. So if you have previous example, then the jointly reducible elements are going to be A and B. But they're not always going to be minimal elements, because you can have something like this. So you can have A, and then B, and then C, and then this is a lattice. But the jointly reducibles are not only A and C, which are the minimal elements, but also B. B is not minimal, it has A below it, but it's still jointly reducible, because you can't write B as a join of anything below B. Okay, so here the jointly reducibles are A and B, and here the jointly reducibles are A and B. Okay.
The divisibility lattice?
So, yeah, that's a good question. So, in the divisibility lattice, you trivially have the primes, which are jointly reducible, because let's look at the divisibility lattice of 12. So, O12. Then I have 1, I have 2, I have 3, and then I have 4, and then I have 6, and then I have 12. Okay? So the primes are going to be jointly reducible, always. But so are going to be the prime powers. So here the jointly reducibles are 2, 2 squared, and 3. And in general, if you look at the divisibility lattice of n, then the joint irreducibles are going to be P1 squared, up to P1 to the alpha 1, and then P2 squared, P2 cubed, up to P2 to the alpha 2, and so on for all the primes. So the building blocks of the divisibility lattice are going to be prime powers. Okay. So just to set up some notation, I'm going to let J be the set of joint irreducibles of L, and Jx, for x being in the lattice, is going to be all joint irreducibles below x. So Jx is just the set of joint irreducibles which contribute towards building x. So now a similar setup as for groups, where what does generating mean here? Well, generating just means if you have an S-tuple of joint irreducibles and you take their joint and you get the top element, then you sort of generated everything. So that's the concept that you use. I'm not going to go through it again, but a similar setup, a similar probabilistic setup gives, and then applying Mobius inversion, gives a probabilistic zeta function for L. So just have x in L, bottom element. So 0, I'm always going to denote this bottom element, smallest element of the lattice. And it's excluded for some stupid reason. And 1 is going to be the top element of the lattice. So then I have cardinality of J divided by the cardinality of Jx to the power x. Okay. And I'll call this the probabilistic zeta function. Okay. So, good question is why do you care? I've given you the probabilistic zeta function of a finite group, and sure that has some probabilistic meaning, and when it comes to generation of groups, and it's probably important. But why do we care about the probabilistic zeta function of a finite lattice? So,
could I just try to understand? So on the top you have
this is
function,
yeah.
and previously this was HG, right? So the G, the group has now, of course, this was because we were considering all the subgroups of the fixed finite group. Now that has been replaced by 1, right? And at the bottom you have replaced the index by
the ratio of the ratio. I replaced the index by the ratio of the total number of joint irreducibles divided by the number of joint irreducibles below x. So we're gonna get there, and so yeah, I'm going to return to this point in just a moment. So I'll say a few words about why do we care, and the reasons are topological. And if you don't understand any of the words that I'm about to say, it's okay, they're not really important. But for the people here who perhaps like topology, I'm gonna say a few words about why we care. So Brown in 2000 was interested in topological considerations of this sort of stuff. So what do I mean by that? Well, if you have a group G, or really if you have a group G, I can form a poset. I can form a partially ordered set out of that. Well, one way of doing that was looking at the subgroup lattice. Another way of doing that is looking at the so-called coset lattice, which I'll denote by C of G. And this is just the set of all cosets of all elements of all subgroups. So X runs over all G, and H runs over all subgroups. Okay? So I just take all cosets and put them together. And the partial order is going to be a containment, set containment. So the relation of being a subset. Now, this is not quite a lattice because there's no bottom element, but I'm going to just attach a bottom element artificially to be the empty set. Because the empty set is going to be contained in everything, so it will be a genuine bottom. Okay, so what an observation, well, before I get to that, if you have a partially ordered set, you can form a topological space out of it. Namely, you can form a simplicial complex by looking at all chains. So what's a chain? A chain is just something which looks like this. Okay, so these are vertices and these are edges. So these are chains. And you have a coset, a set with partial order. You look at the set of all chains. That naturally forms a simplicial complex, whatever that is, it doesn't really matter. And that gives rise to a topological space. And the remarkable thing is that if you look at P, the probabilistic zeta function of G, and evaluate it at -1, then this is the reduced Euler characteristic of the coset lattice of G, viewed as a topological space. So if you don't know what the Euler characteristic is, then it's a cool thing in topology, which it's okay if you don't know it. You should definitely look it up. The remarkable thing is that from G, you go to a topological space, and then you can recover some information about the probabilistic zeta function evaluated at -1 from the Euler characteristic. Now the natural question is, and this is due to Brown, well, both the question and the answer are due to Brown. Can you recover? So again, if you didn't understand the words, it's fine. The point is, P of G -1 can be recovered from some topological information of the group. So the question now is, can you recover P of GS for all S from this coset lattice? Okay, so we use the coset lattice to get the value at -1. Can you get the entire function? And the answer is yes. And again, this is due to Brown. But he was only interested in coset lattices. So what we did is we took this setup and we said, well, let's forget about everything. And let's just look at the probabilistic zeta function of a finite lattice in its own right. Let's forget about all the motivation and all of this stuff. We want to extend the definition of the probabilistic zeta function to all lattices, which is what I gave there. And now we only care about that function in its own right. Okay, but this is some motivation for why you would care about this. And moreover, so why is the answer to this yes? Well, the probabilistic zeta function of the finite group G can be recovered by the coset lattice by simply shifting. So this is the probabilistic zeta function of the group. This is the probabilistic zeta function of the lattice. You have to shift the parameter by 1 because of a technical and unimportant reason. But the point is that you get the entire function. You get all of P of GS from plugging in the coset lattice. And this is a good point. So one might be tempted to think that the lattice you would plug in here is the subgroup lattice. So in that sense, it's not exactly replacing H with X and 1 with a group. And then, because this won't really make sense, why? Because if you look at the subgroup lattice, what are the joint irreducibles, or the building blocks? Well, they're minimal subgroups, blah, blah, blah. But that's not the initial setup. The initial setup is we have elements and we're letting them generate. We don't have subgroups and things like that. But here, if you look at the joint irreducibles of the coset lattice, then they're just cosets of the identity subgroup. Cosets of the trivial subgroup. So they correspond to elements of G. And so this is a more natural candidate to plug in the definition of the probabilistic zeta function of a finite lattice, and it gives you the probabilistic zeta function of a finite group. So this definition for lattices is more general. It encapsulates all groups in particular, all finite groups.
Does that explain why you included the middle element there?
Yeah, so the reason for that is just, if you look at joint irreducible elements and you let them generate by taking joints, you're never going to get to the bottom element. And yeah, it's a good analogy with this one. It just here, the bottom element is the empty set. Who cares about it, right? You just never get it. Okay. So let's recall the divisibility lattice. This is just a set of divisors of n. And I'm going to assume here that n is square free. If n is not square free, I still have an expression for the probabilistic zeta function, but it's more complicated. So let's look at what the probabilistic zeta function of the divisibility lattice looks like. And by the way, the divisibility lattice is the subgroup lattice. So this is also the subgroup lattice of the cycle group Z modulo n z. So this is, what I'm trying to demonstrate here is, what do you get if you plug in the subgroup lattice? So what do I get here? I get -1 to power r times the sum of k from 1 to r of -1 to the k, r choose k, divided by r divided by k to the power s. Okay? The thing is, this is not an ordinary Dirichlet series anymore. As k runs from 1 to r over k is typically not going to be an integer. So it's a so-called generalized Dirichlet series. And there are more general notions than this, but for us, we're always going to get, these things are integers, so we have ratios of integers, so we're always going to get rational numbers. So I'll just have a sum over all q and q of aq divided by q ds. So I'm extending from integers, the Dirichlet series from integers to rational numbers. Okay? And now I'm going to give a definition, and really, I don't have a good motivation for why you would care about. So the question now is, when do you get ordinary Dirichlet series? You certainly get ordinary Dirichlet series when you plug in the cosine lattice, because you get the probabilistic zeta function of a finite group, and the probabilistic zeta function of a finite group was an ordinary Dirichlet series. And really, I don't have a good motivation for why you would care about this question. For me, it was an excuse to do some number theory. And maybe there are more important reasons why someone would care about this. But anyway, I'm going to say a lattice L is strongly cosine-like if these ratios that appear are always integers. So if jx divides the order of j, the number of joint irreducibles, the number of building blocks below x, divides the total number of joint irreducibles, the total number of building blocks for all x. So this will certainly guarantee that these are all integers, so I get an ordinary Dirichlet series. But in principle, this need not be necessary, right? I have these Mobius numbers on top, and as we saw in the example, they tend to alternate sign. We've got 1, and a -1, and a 0. So perhaps some cancellation happens around here. And then something that is not an integer ratio disappears because of things cancel. So the other definition is, I'm going to call lattice L, and I'm going to abbreviate strongly cosified as SCL. And the other definition, so lattice L is weakly cosified. And I'll abbreviate this as WCL. If P of LS is an ordinary Dirichlet series. Okay, so strongly cosif-like certainly implies weakly cosif-like. And the natural question is, what about the other way? Are maybe these two definitions the same thing? The answer is no. You have lattices which are weakly cosif-like, for which if you compute the probabilistic zeta function, then it looks like it is an ordinary Dirichlet series, but there are some non-integer ratios. There are some purely rational ratios. There's more to this story, but I won't say anything about it unless someone asks in the end. So yeah, let me just move on. Okay, so the reason for the name is hopefully, I mean, sort of hopefully clear. Cosine lattices always satisfy both properties. So I'm sort of saying, well, if you have some sort of structure like this, then maybe you are close to being a cosine lattice. At least you would hope for that. So now I'm just going to briefly go through two examples in the context of analyzing these properties. So one is going to be the partition lattice. By n. So this is going to be all partitions of 1 through n. Ordered by refinement. So partitions is I just take the set 1 through n and I split it into disjoint subsets. What do I mean by refinement? Well, let's just look at maybe n equals 5. So if I have a partition like this, then I can refine it by taking one of these sets and splitting it further. So this is going to be greater than 1, 2, 3, and 4, 5. Because I've taken this set and I've split it further. But this thing on the left-hand side will not be greater than 1, 2, 3, 4, 5. Okay, because what I've done here, I've split this, but then I've taken the 3 and put it in another set, and that's not allowed. That's what I mean by refinement. You're only allowed to take a subset and partition it further. You're not allowed to combine elements. Okay, so I won't go into details, but the structure of Jovian crucibles here is additive. In the sense that, if you look at the number of Jovian crucibles below a given element, then it's a sort of sum. But here I have a divisibility condition, I have some multiplicative structure, and addition and multiplication generally don't behave so well with each other. Because of this, it's natural to expect that if D true, I won't call this a theorem. The proposition is that pi n, the partition lattice, is strong cosine-like if and only if it's weak cosine-like, if and only if n is small. So n is at most 4. Because it's just, when n is at most 4, just too small that nothing interesting can happen. But once n is at least 5, then pi n doesn't have this nice structure. This is a trivial result. There's nothing interesting to it, but the interesting thing.
May I ask a question? So here the statement of the proposition is that the two notions coincide or are equivalent if and only if n is less
No. So no. The statement is pi n is strongly cosine-like if and only if pi n is weakly cosine-like if and only if n is at most 4.
Okay, but so it means in this case the two notions coincide, but if n is greater than
they still coincide.
okay, so this is not a counterexample.
No. So strongly for partition lattice and strongly cosine-like and weakly cosine-like are the same thing for all n, and it is strongly cosine-like if and only if n is at most 4. Okay. The important thing here is that pi 4 is the first example of a strongly cosine-like lattice, which is not isomorphic to the cosine lattice of the group. So if you look at pi 1, pi 2, and pi 3, they're all cosine lattices of groups. So of course they're strongly cosine-like. But if you look at pi 4, it's not cosine lattice. I think I'm running out of time, so I'll take 3 minutes to give the more interesting result.
And the proof here is case-by-case analysis, or what's the?
Yeah, so the proof just really finds an element for which you always have a non-zero Mobius number on top, and such that the ratio is not an integer. It's very easy to find, but it's completely trivial. Really. There's nothing interesting going on here. But more interestingly, we then looked at the d-divisible partition lattice. So this is pi d and d, and this is partitions. So again, I take a set and I split it into disjoint subsets of 1 through dn, and it will be clear in a second why I need this to be divisible by d, such that every part has size divisible by d. Okay? So, of course, if every part has size divisible by d, then I add all of them up. This thing is still going to be divisible by d, so I need the number of elements which is divisible by d. Okay? And the interesting thing here is that when d is at least 2, the structure of joining reducible elements completely changes. It's not at all, it doesn't resemble the partition lattice at all. So the structure of joining reducibles is now multiplicative. And again, what do I mean by this? I mean, if you look at the number of joining reducibles below a given element, then it will be a product rather than a sum. So one might expect that here you do get something that's strongly cosine-like or weakly cosine-like, and there are actually, for reasons which I don't understand, but my supervisor did, there are topological reasons to believe that this will be strongly cosine-like because the d-divisible partition lattice is topologically very similar to cosine lattices. So one might expect that you get a positive result here. However, I'll call this a theorem. For any d greater than or equal to 2, there exists some n depending on d, such that pi d and d is not strongly cosine-like for n greater than n. Okay? So this is saying asymptotically, as you go to infinity, this thing is not going to be strongly cosine. And how do you prove this? I certainly won't make an attempt to prove it here, but I'll just say that what pops up here is considering divisibility relations of central binomial coefficients, 2dm to dm. So you ask, does this number divide the central binomial coefficients 4dm to 2dm? And in order to answer this question, it suffices to locate primes in short intervals, in suitably short intervals, which are sort of carefully chosen, so that the prime divides the left-hand side, but not the right-hand side. And for this, it's enough to use the prime number theorem. It just gives you the length of the interval is enough so that you get something like this. The reason I like this is that oftentimes in number theory, and especially in first force number theory, when you're looking at primes, you look at such divisibility conditions without any sort of motivation. You're just like, oh, here's some magic, and they are somehow relevant to primes and give some results. But here they pop up very naturally. If you're willing to accept everything else as natural, then these divisibility conditions pop up very naturally, and you're thinking about central binomial coefficients and primes. Okay, I'll stop. Thank you.
Thank you. Can I read? Thank you for this wonderful talk. Now is the time for questions. Lite 2 minuter.
Je to do naš teraz jakini last, da podani numru joiner reducibles, a teraz okay, funcționi von mangul first, esențialești indicator i okay, ăsta log p if n is a prime power, log p of which weight esențialește acest indicator, przy czym możemy definium nie funkcjonality per Lattices cu Prishtina se joiner reducibles na siguri descanso sto currency da numru joiner reducibles na Lattice. Asta este jakimi familie Lattices a nie różne uniformne statowe. No chodzi o dog. To nie know what to do with speed.
geldi ve shumë personer për operativin e tij edhe shpresoj që të ftoj kafe herë të tjera. Faleminderit. Tash të regoj, nëse keni për kafe e iniciuar.